Hello, we are Group 33 of the Modeling and Robot class for the fall of 2015 with Dr. Tosunoglu. Our group consists of Vega, Francisco Sanchez, and myself, Miguel Gutierrez. Today we are going to be presenting about the 4-bar mechanism analysis and the synthesis of a slider crank mechanism. So for our overview, what is a mechanism? Our 4-bar mechanism analysis and the synthesis of a slider crank mechanism. So first of all, what is a mechanism? A mechanism is a part of a machine which contains two or more pieces arranged so that the motion of one compels the motion of the others. They are generally used to change directions of movement, change the type of movement, change the speed of movement, or to change the amount of torque. This is our problem statement. First, we have to analyze a given 4-bar mechanism and animate its movement. Second was to synthesize a slider crank mechanism given 3 position coordinate lines and animate its movement. For our motivation and goals, we wanted to master our skills required to analyze a 4-bar mechanism and to successfully design and animate the mechanism to a realistic degree. Also, to learn more efficient methods of slider crank mechanism synthesis and to be able to create a realistic animation of the synthesized slider crank. Division of responsibilities. Vega worked in the synthesis of the slider crank, writing the report and presentation. Francisco worked with the 4-bar mechanisms analysis, SolidWorks animation, and synthesis of the slider crank. And I worked with the synthesis of the slider crank, report writing, and video editing. Now we're going to talk about the 4 mechanisms analysis. As a group, we have to analyze a given 4-bar linkage, finding all joint motions by dividing the motion into 1-degree steps. We had to calculate the unknown joint velocities and acceleration for the first closure and plot them as a function of the input joint position. We also had to determine practical, realistic application for the mechanism, and lastly, create an animation of the mechanism motion. This is the given parameters to our problem. And now, we will be talking about the position analysis.
Hello, my name is Vega, and I'm going to speak about the analysis of our 4-bar mechanism. For our position analysis, we began with a position equation shown here. From these, we came up with these 2 equations in order to get R3 and θ3 by themselves. Lastly, we eliminated the unknown θ3 in order to get the long R1 bar equation here. The next step was to determine θ4 for each point in the motion of the linkage. So these equations were applied to each degree of θ2 from 0 to 360 degrees. These equations gave us values for A, B, and C that are necessary for the next step. Also shown here are some sample values for our calculation of these variables. When we have determined A, B, and C, they are then plugged into this quadratic equation D, shown here, the result of which is used to determine θ4 for each degree of motion through both closures of the mechanism using this equation. Shown here are some sample calculations for θ4. From the known values of θ4, we can derive the values of θ3 from both closures, using this equation here, utilizing values of θ1, 2, and 4 that we have previously tabulated. Also shown here are some sample calculations for θ3. And finally, the coordinates of the coupler link joints for A and B were calculated using these 4 equations that utilize θ2 and θ4 and as tabulated previously. The trajectory of point S was then calculated. The 2 equations shown here allowed us to find the points xs and ys using known lengths and θ values. Sample calculations are also shown. Shown here is the trajectory traced by point S when each point of xs and ys were plotted on a graph. Now for the velocity analysis of the 4-bar system. These formulas here are used to calculate omega values for velocity 3 and 4. From these equations, we derive the equations shown here to get the unknowns together and to obtain the R2 dot equation. Having R2 dot as an input, This matrix is used to solve for omega 3 and 4. To solve for these velocity values, the determinants and the inverse matrices of the A matrix were found. Finally, this equation was put together to solve for omega 2 and 3. Shown below are sample values for the calculation of these values. Shown here is a plot of omega 3 versus theta 2 for the full range of motion of the mechanism. As you can see, the velocity returns back to its origin point after the full range of motion. And shown here is the same plot for omega 4 versus theta 2. Again, the velocity returns to its original point. For the acceleration analysis, first we use the data previously obtained in the velocity analysis and plug them into these equations shown. From there, we distributed R3 and R4 to one side and obtained these equations shown. Having R2 as an input and A3 and A4 as an unknown, we set up this matrix here. As before, we then found the determinant and the inverse matrix of matrix A. And finally, we are able to solve for A3 and A4 using the completed equations shown here. Also shown are some examples of our calculated values. Shown here is a plot of A3 versus theta 2 through the full range of motion. As before, the acceleration returns back to its origin point after the full range of motion is completed. And shown here is a plot of A4 versus theta 2. Again, it returns to its original point. As for the application of our mechanism, we decided that one potential use would be for a sort of device stand for smart devices in which you can have an adjustable viewing angle of the screen. And here is an animation of the mechanism in motion. And now to speak about the slider crank portion of our project is my teammate Francisco Sanchez.
Hello, my name is Francisco, and I'll be talking to you about the slider crank mechanism synthesis. For the second part of our project, we synthesized a slider crank mechanism that would pass through the points indicated here. Our first attempt, using the mathematical method, yielded unuseful results, and multiple attempts at this method were unsuccessful. The synthesis was able to be performed successfully using SolidWorks to aid visually and geometrically. The given points A and B, 1 through 3, were sketched to represent the 3 required positions of the mechanism. Using the perimeter circle command, a circle was created that would pass through all 3 A points, whose radius would be equal to R2. This image shows points A and B1, A and B2, and A and B3. Pole positions were then found by sketching lines between respective A and B points and sketching the perpendicular bisectors where these intersect, represent the pole positions P12, P23, P1, and P13. These are found using the measuring tool. By mirroring P23 above the line formed by P12 and P13, we find the image pole position P'23, and by sketching a circle through it, P12 and P13, we find the circle of slides with radius 583. We then placed a point on the circle of the slides that would represent C3 so that CX3 would equal 4. By measuring, we found that CY3 is equal to 9.28. Using these equations, the local coordinates for C3 were determined, and using these, points C1 and C2 were calculated. This image shows the final synthesis for the 3 positions. It also shows that C1, C2, and C3 fall on the same line. Here we show the motion analysis from the SolidWorks, which show the mechanism moving through the required positions. This type of mechanism is commonly used for indexing movements, such as feeding a single unit through a production line, as we see here with this image. Lastly, this video shows an animation of a slider crank mechanism. Thank you.
No?